When testing chips in production, measurement system error is your enemy. It can make a good part look bad, resulting in lower yields as you throw away parts that are actually good. Or even worse, it can make a bad part look good, resulting in a field failure, which is costly in many ways. Since a gauge study is the gating item to production testing, spending less time running and debugging after the results of a gauge study can get you to market faster, giving you a leg up on competition and increasing your bottom line. The most common method of understanding and improving your measurement system error is by running a gauge study. This analyzes the repeatability, which is how accurate can the same system measure the same part, and reproducibility, which is how accurate can different testers, load boards, sites, all measure the same part of your measurement system. The main metric used for the result of the gauge study is an R&R %, which is a function of your repeatability and reproducibility. Generally speaking, if it's over 30%, it needs to be investigated further and resolved if possible. Now, however, many industries use gauge studies, and many of the measurements taken don't have any spec limits. In those cases, R&R % is the golden standard. However, in the product and test engineering world, we have test limits for the parameters we're measuring, and we can use this as an advantage in gauge studies to reduce chasing our tails, debugging time, and getting to market faster. What if I told you that this test had an R&R % of 46%, mainly due to the tester-to-tester reproducibility? Since it's over the 30% threshold, you'd need to spend a lot of time debugging and trying to fix the issue with experimenting with new matching components on the board, or wait time, or test methodology changes, and how the test was run. But we have the luxury of having test limits. What if I zoomed out and showed you where our typical measurements are in relation to the actual test limits? Here you can barely see a difference in the results now, and in relation to the test limits, with a CPK of roughly 15, do you think the tester-to-tester reproducibility would be an issue in production? Absolutely not. Since we have this luxury of having test limits, we can use a more meaningful metric called the precision-to-tolerance ratio. This is very close to the Gage R&R formula, but instead of dividing the R&R, which is repeatability and reproducibility, by the limitless total variation, it divides it by your limit space, which is your upper limit minus your lower limit. So if the R&R % was an alarming 46%, over the 30% threshold, which needs investing time into debugging the quote-unquote issue, what do you think the precision to tolerance % is, or P to T ratio? Go ahead, make a guess. Well, it's a whopping 1.81%. So what does this really mean to you as a product or test engineer? It means you can spend less time chasing your tail, debugging your gauge study results for quote-unquote issues that aren't really there, since you have the luxury of test limits and performance results. In fact, in this part's data, a normal gauge study R&R % flagged 53 tests as being over the 30% threshold, whereas the P to T ratio only flagged 1. That could save you weeks or even months of wasted debugging that isn't even necessary. Now, gauge studies can be performed using many different tools. Now, when doing so, use the P to T ratio with your data that has test limits, and then go enjoy all that extra time not spent debugging out on the beach. Now, Galaxy's Examinator also has the ability to run gauge studies with either R&R % or the precision to tolerance ratio, so you can see the difference for yourself, and you can even start a new free trial today. So click to learn more down below, or go to galaxysemi.com.